All right, you guys, let's finish talking about confidence intervals. So for the first portion of this week, we're going to be dealing with confidence interval for population proportions. All right, so we're going to want to find what's called a point estimate. So before we've been using X bar, or the sample average, to build a confidence interval around mu, our population mean. So now we're going to have a new point estimate, and we're going to construct a confidence interval for what's called this population proportion. Okay, so the probability of success in a single trial of a binomial experiment is called the population proportion. Okay, it is denoted by this italicized little p. Sometimes you will see it used as the Greek letter rho, the lowercase Greek letter. The point estimate for p, or the population proportion, is the proportion of successes in a sample. And we're going to use p with this little caret on top of it, and it's read p hat. Okay, and we're going to calculate this proportion or fraction by taking the number of successes as our numerator and letting our denominator be the sample size. Okay, so again, we're going to estimate the population parameter, which is just plain old p, the proportion, using the sample statistic p hat. All right, the point estimate for q. All right, so you've heard mind your P's and Q's. Well, it comes from math. P is the successes, Q is the failures. So this italicized Q is the population proportion of failures. And we're going to estimate that with Q hat, which is just 1 minus P hat. All right, so P hat is the proportion of successes. If we want the proportion of failures, we're just going to subtract our successes from 1. All right, so let's look at an example. I think this is when it best starts to make sense what the heck I'm talking about. In a survey of 1,000 U.S. adults, 662 said that it is acceptable to check personal email while at work. Find a point estimate for the population proportion of U.S. adults who say it is acceptable to check personal email while at work. Well, shoot, you guys check personal email probably when you're in face-to-face sessions with me. But anywho, all right, so what do we need here? We need to calculate the population proportion from this sample. All right, so we have 1,000 U.S. adults. That's our N. All right, that's the size of the sample is 1,000. 662, that's going to be our number of successes. These are the people who said it's okay to check personal email at work. So if we want p hat, we're just going to let 662, our successes, be our numerator, 1,000, our sample size, be our denominator, and when we plug that into our calculator or Excel, we get 0.662 or 66.2%. All right, a confidence interval for a given confidence level for a proportion population is going to be very similar to what we've been doing. All right, we're going to add and subtract some margin of error to our sample statistic p hat. All right, you guys will probably be happy about this. We're not really going to use Excel too much except to get this critical z value right here. All right, we'll actually be calculating this square root of p hat times q hat divided by n, either in our calculator or Excel. Okay, the probability that the confidence interval contains p is going to be our confidence, or our C. All right, so let's step through the recipe. How are we going to do it? We're going to identify our sample statistics N and X, so the sample size and the number of successes. We're then going to calculate our point estimate p hat by getting that fraction of x over n. We're going to verify that the sampling distribution for p hat can be approximated by a normal distribution. So this is an important point to make. We can't just assume we're going to use a normal distribution. We can't always use a normal distribution. There's a little check we need to do. All right, and what is that check? We are going to take our sample size n and multiply it by p hat. If we get a number that's greater than or equal to 5, when we do this, as well as when we do n times q hat, then we can approximate our sampling distribution with a normal distribution. All right, then we want to find the critical value, z sub c, that corresponds to our given level of confidence. So here I'm giving you guys exactly what you'll type in Excel, and I'm saying, okay, the ABS is kind of new. I haven't thrown that at you guys yet, but that's just absolute value. I'm just saying that if we were to just type in norms n of 1 minus c divided by 2, then what we're going to get is the negative z, and you're more than welcome to just type that in and just know, hey, I'm going to need the positive version of this number, or you can just type absolute value of what you're calculating with norms n, and you'll always get the positive z. All right, then once we have our critical z from Excel, we're going to multiply it by the square root of p hat times q hat divided by n, and this is going to give us our margin of error. This number e, all right, whatever this margin of error is the width of our fence, or the width of the confidence interval. We're going to add it and subtract it to p hat to actually get the confidence interval, the endpoints of the confidence interval. All right, so let's go through an example. All right, going back to where we just calculated our sample statistic, and our survey of 1,000 U.S. adults, 662 said that it is acceptable to check personal email while at work. Construct a 95% confidence interval for the population proportion of U.S. adults who say that it is acceptable to check personal email while at work. Okay, so step one, all right, was to figure out x and figure out n. All right, we know x is 662 from our problem here. We know that our sample size is 1,000. Okay, what are we going to do from here? Well, we need p hat. All right, p hat is x divided by n. Oops. All right, so, and I'm just going to tell you here, this is x divided by n. That's how we calculated it. All right, so I have p hat. All right, now I need, I'm going to call it critical z. All right, critical z is equals absolute value of norms n, so we need to get the z-score, all right, given some probability. What is the probability? It's 1 minus our confidence, 0.95, divided by 2. Okay, so this is norms n of 1 minus 0.95 divided by 2, and of course I did the absolute value of that. Okay, so I have my critical z. All right, I also need, I'm going to move this down, I also need q hat. Okay, this is 1 minus p hat. All right, so this equals 1 minus p hat. So you can see we have our p hat, we have our q hat. All right, can we approximate our distribution with a normal distribution? So I need n times p hat. I need n times q hat. And I need to get a number bigger than 5. So n times p hat, so that's 1,000 times my p hat. Okay, and I say yes, because yes, it's greater than or equal to 5. All right, n times q hat. All right, again, yes, this is greater than or equal to 5. So yes, we can use a normal distribution here. Okay, so we know that we can use a normal distribution, and I apologize for the dog barking in the background. Rest assured he is appropriately duct taped at this point. All right, so we want to calculate our margin of error. Okay, so using our formula here, we have critical z, so equals critical z times the square root of p hat times q hat divided by the sample size. Okay, so again, that is critical z times the square root of p hat times q hat divided by the sample size. And we get approximately 0.029. Okay, so I'm going to write this out here. This is z times the square root of p hat times q hat divided by n. Okay. All right, so now we want to get our left and right endpoint. So our left endpoint and our right endpoint. The left endpoint is equal to p hat minus the margin of error. Our right endpoint is equal to p hat plus the margin of error. Okay, and I'm going to turn these, well, I'm going to turn these into percents so we can see them a little bit better. So we can see that we are between 63 and 69%. So what's this saying? This is saying that with 95% confidence, you can say that the population proportion of U.S. adults who say that it is acceptable to check personal email while at work is between 63.3% and 69.1%. Okay? Once again, you can see I've gone over this before, but when you want to see decimals, all you have to do is click up here, increase the number of decimal places, and so there we are seeing more decimal places. Okay, let's go back to the slide. All right, so sometimes, as you guys know, because we did it a couple weeks ago, given a confidence level and a margin of error, we want to find the minimum sample size needed to estimate our parameter. Okay, little dog's now on Craigslist. No, that is not Jordan. That is a little ankle biter. All right, so anyway, as I was saying, we do want to sometimes be able to calculate the minimum sample size n needed to estimate our population parameter. Okay, so how are we going to do this? Guys, we're just going to need to use this formula. The minimum sample size is going to be equal to p hat times q hat, all right, times, and this is where we're going to have our critical z divided by our margin of error, and we're going to square that number. Okay, no worries. Again, you know that on exam 3 you'll be able to have a note card, so you're just going to want to have this formula on your note card. Okay, and notice this formula assumes you have an estimate for p hat and q hat. All right, this is not always going to be the case. Okay, we will either have that estimate in the problem, or I'll say no preliminary estimate is available, in which case you use p hat and q hat as both 0.5. All right, so let's run through an example doing it both ways. You are running a political campaign and wish to estimate with 95% confidence the population proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of the true population proportion. Find the minimum sample size needed if no preliminary estimate is available. Okay, so we have no preliminary estimate. That means we're going to use p hat and q hat as both 0.5. All right, so here we have our confidence of 0.95. We know from the prior problem this is 95% confidence again. So we've already calculated in Excel with norms inv that critical z is 1.96, and our error is 0.03. Notice it's given to us as 3%. I'm not going to use the integer 3, all right? That error is going to be, I'm going to use 0.03. Okay, and so here I'm just plugging my numbers into my formula. All right, so again, since I don't have preliminary estimates, I'm using 0.5 for both p hat and q hat. My critical z of 1.96, all right, my error of 0.03, all right, and I plug all this into my calculator or Excel, and I get approximately 1067.1. What are we dealing with here, guys? We're dealing with registered voters, right? So is it possible to have 0.11 of a registered voter? Heck no, right? So what are we going to do? We're going to round up to the nearest whole number. So with no preliminary estimate, the minimum sample size should be at least 1,068 voters. Okay, let's run through it again, but this time I'm going to tell you we have a preliminary estimate that gives p hat as 0.31. Okay, so how does that change things? Well, if we have p hat is 0.31, in order to get q hat, we need to subtract 0.31 from 1 to get 0.69. So again, we have p hat, we have q hat's 0.69. All right, we have our same error and our critical z and our confidence. So now with this preliminary estimate of 0.31, I'm changing my p hat and my q hat. Right, so I have 0.31 times 0.69, and then I again have the critical z divided by the margin of error all squared, and this time I get 913.02. Again, we have to round up to the nearest whole number. So if I have a preliminary estimate of p hat as 0.31, then the minimum sample size should be at least 914 voters. Right? Obviously, we need a larger sample size if no preliminary estimate is available. That's why we're using the estimate of 0.5 when we don't know it. We're going to say, okay, well, we're going to allow for the greatest margin of error and get our largest sample possible.